I would like to tell you about what I intend to say miraculous things, but that's not the right word. The rather wonderful things that have enabled us to be here in this lovely church today, but also to illustrate some of what I think is the beauty of our universe, because that's relevant to the very last thing I want to say. So let's begin, I think. If you can go to somewhere on a very dark night when there's no moon, you can look up to the sky and you can see what we call the Milky Way, which is our view of our own galaxy. It contains about 100,000 million stars, and our sun, of course, is just one of them. The ancients, a couple of thousand years before Christ, split the stars that we can see with our unaided eye into what we call constellations. And a long time ago, people like Helvelius here drew wonderful star charts. In fact, they were a bit hard to use because they were done back to front, as looking from the outside in. This is Orion the Hunter, and one thing, of course, is that these lovely drawings make it rather hard to see where the stars are, but it is, in fact, sideways flipped over, and that's, in fact, how we see Orion. The three stars of Orion's belt pointing down to the star Sirius, which we see low in the south in the winter evenings. And then they point up towards the lovely constellation of Taurus the Bull, with Aldebaran, the eye of the bull. Well, on the left there is not a very dramatic diagram that I've drawn of Orion, but to the right you see hopefully a lovely picture. Here are the three stars of Orion's belt, and below which we have the sword of Orion. If we home into that sword, we see a lovely region of pinkish nebulosity. The coloured light comes from excited hydrogen in much the same way that we have our sodium street lights, which look an orange colour. Now they're excited, the sodium atoms are excited by electrical discharges. Here, in fact, it's ultraviolet light from the very, very bright stars at the very heart of the Orion Nebula. This is the nearest region of star formation to us. It's a stellar nursery. And in the dust clouds here, stars are forming as we speak. It's impossible to make one star at a time. You have to make groups of stars. And so we then see lovely little clusters in the sky. This is the Pleiades cluster, perhaps the most beautiful, a lovely object in binoculars that we see up to the right of the head of Taurus the Bull. It's in Taurus, up to the right of Orion. And in fact, you can also see dust scattering the light from those young, very bright stars. So stars like our sun are born in stellar nurseries like the Orion Nebula, and initially are in little star clusters like the Pleiades. Well, there's a fairly dramatic view of our sun some years ago, at a time of what we call solar maxima, when the sun is very active. There are lots of sunspots and there are lots of flares, like you can see down here. Now, the outer parts of the sun we can't normally see, but I was lucky enough to be in China in fact, the 1st of August, when we saw an eclipse of the sun. This is a photograph of it, and you can see these lovely streamers streaming out from the sun. It's called the solar corona, but the sun is boiling off, a solar wind as it's called. When those particles come to our Earth, they can interact with the atoms in the upper atmosphere, oxygen and nitrogen, and produce this lovely effect that we call the aurora borealis. And if you can ever go to actually see that, then I would certainly recommend it. It's an absolutely wonderful sight when you can. Those are two images of the sun, and if you look at the date, they're yesterday, taken by the SOHO observing spacecraft. And I think you'd agree, the sun on the left is looking very bland, and there's almost nothing visible really. A few little prominences here on the right. This is called H-alpha, looking at the surface in more detail. We are actually in the middle of a very deep trough between the last solar cycle and, we assume, the next one. The time between the end of that one and now is getting longer as we speak. It's now around 500 days. It's about the longest, certainly in recent times. And the measurement of the solar wind, the solar activity that we measure here at Earth, is lowest that has ever been recorded. Now, providing nobody records this, I will say, because it's heretical, that could be because there's a bit of a link between the sun and the Earth's temperature. I'm not allowed to say this, but currently the Earth is cooling down. I know that's not correct, but it is. And it may just be, maybe not correct to say, it may be that there is, in fact, a link between solar activity and the Earth's temperature. There was a time in the late 1600s when the sun had no sunspots for about 30, 40 years. And at that time, I don't know if anyone here in London can tell me, but the actual Thames froze. They used to have ice fairs. So although it's now very often stated not to be true, I suspect it's not just the CO2 we produce from our cars and everything. There may well be other things as well that affect global warming. But we wait to find really the beginning of our next solar cycle. Well, it's at the heart of the sun I really want to begin. The only reason we can be here is because our sun, at the present time, is converting hydrogen to helium and so producing energy by nuclear fusion. I also used to love, about 10 years ago, you used to see two CVs, you know, the little lovely cars, and on the back was a yellow poster with a smiley sun saying, "Say no to nuclear power." Do you remember those? And of course, that's where our power comes from, although of course it's fusion. So it is the very act of converting hydrogen to helium in the core of the sun at about 15 million Kelvin that's generating the heat and the light that enables us to exist here on Earth. Now, that process is really quite amazing. What has to happen is that two hydrogen nuclei, two protons which are positively charged, have to get close enough so that quantum mechanically they can tunnel through their potential repulsion barrier, because like charges repel, and get close enough to convert into something called deuterium, which is a proton and a neutron. And that's the critical key stage in producing helium, which is the end stage of the nuclear fusion process. Now, in that quantum tunneling, there is an exponential term and with temperature. And what it means is this, that a very slight change can make things very, very different indeed. Things wouldn't have to be very different in our universe for that reaction to go far faster than it does now, as it is in our own universe. If it did, our sun would burn up its fuel far more quickly, perhaps in 1 billion years, not 10 billion years. And then we would not believe there'd be time for human life to have evolved. Conversely, if that reaction rate was, say, a factor of 10 slower, our sun would be very dull, and we couldn't get warm enough. So in the same case, we couldn't be here. So it's a very finely tuned reaction that enables our sun to remain stable and produce energy at an approximately constant rate. It's getting hotter over a period of getting on for 10,000 million years. We're about halfway through at the present time. Another key thing is that it is very hard to get from helium to the next element that can be created and is stable. Helium naturally would produce beryllium-8, 2 helium-4s, beryllium-8, but that's incredibly unstable. And it's only if you can get 3 heliums to come together almost instantaneously, you can get to a stable nuclei called carbon-12, which is then the next element that's created in stars in the latter phases of their life. So it's perhaps not surprising that carbon makes up a lot of us. In fact, the next element beyond that is another helium-4 plus a carbon-12. You get oxygen-16. If you take hydrogen, oxygen, and carbon, that makes up an awful lot of our human bodies. And another process in slightly more massive stars than our sun produces nitrogen. So we humans are made essentially of the most common elements in the universe. Now, they are created within stars. And the good thing about the difficulty of getting to carbon is that it takes the temperature in the core to rise to about 100 million degrees for that reaction to happen. So if you're at 15 million, there's a big gap. If there wasn't a big gap, the sun would probably start creating carbon and oxygen near the beginning. It would essentially blow up. So there are a lot of things that have to be just right to enable our sun to create the elements within it that actually form up our human bodies. So, as I've said here, if the nuclear fusion process was more efficient, our sun wouldn't live long enough for us. If it was less efficient, it wouldn't be warm enough. We couldn't be here. If helium could turn into carbon at lower temperatures, there wouldn't be a stable phase where the sun spends its life giving us heat and light. But there's another point. If those elements stayed within the star, there'd be no way we could be here either, because our universe began with just hydrogen and helium. And the wonderful thing, of course, is that at the end of their lives, stars blow up. This is roughly how our own sun will appear, perhaps in about 6,000 million years at the end of its life. The central core of our sun, then composed largely of carbon and oxygen, will collapse down until it's about the size of the Earth. It becomes what's called a white dwarf. Probably shouldn't say that anymore, a white vertically challenged object. But anyway, a very small white object, very, very hot. So it's white and blue-white, but the outer parts of the star are blown off into space. The color red you see there comes from oxygen, as does some of the green, but the blues and greens also come, from hydrogen, but the blues and greens also come from oxygen. So we can actually see the fact that elements have been created in the stars, and at the end of their lives, they blow up and they're thrown out into space. Now, stars like our sun can't actually make elements much more massive than, let's say, oxygen, perhaps a touch more. More massive stars might produce silicon, which of course is very common, sand, silicon dioxide. But it's only when you get the most massive stars that we get the heavier elements. This is another one of those lovely planetary nebulae they're called. There is the little white dwarf, this is the surroundings, and you have to imagine this is the fur of the Eskimo's parka. If we look up into Taurus, not far from the Pleiades in fact, there's a little blob of light that was first seen in the year 1054. And it's what we call a supernova, a star that becomes so bright it's visible in broad daylight. It's written in the annals of the Chinese. Now, people in Europe must have seen it as well, but no one wrote it. Now, who were the people that were keeping records? They were monks, but they were, of course, part of the church. And the church teaching was that the heavens didn't change. So perhaps they felt they shouldn't write about it. They must have seen it. Well, this is how it looks now. And the important thing for today is that during the explosion that created this wonderful image, there are lots and lots of very high-speed neutrons which build up the elements beyond iron. So all of the heavy elements, perhaps someone's got some silver or some gold, they're nice elements. Perhaps the less nice elements, such as plutonium, uranium, were also created in just a few seconds as these stars come to the end of their life. But as the material spreads out into space, it enriches the space between the stars, and then later stars can form out of the dust and the gas, and there's enough of the heavy elements like silicon and iron to form dust clouds around those stars, out of which planets like our own Earth were formed. So if stars did not become unstable and explode, we could not exist. So where might we find life? Well, we know it's here on planet Earth. Let's look at this in a little bit more detail. We live in a solar system, and that gives you some idea of the scale, and we are about there on the Earth. We're in what is called the habitable zone of our solar system, where it is not too hot and not too cold, just like baby bear's porridge. So the temperature within this green strip is where you could allow liquid water to exist on the surface of a planet. Now, is that important for life? Well, we're made up basically using a lot of water as a liquid, using the chemistry of carbon. Because, as I've just said, carbon, oxygen, nitrogen, hydrogen are the most common elements in the universe, it's probably true that most other life forms are based upon the same chemistry as we are. And of course, carbon, I believe, is the most reactive, the most interesting, shall we say, of all the elements in terms of what it can produce as compounds. So it's quite likely other life forms would require similar temperatures where water is a liquid. Well, you can see the Earth is nicely in the middle of our habitable zone. Mars is just on the outer edge, which implies now it's too cold. But of course, that may not have been true in the past. You may have heard of Percival Lowell. With his telescope at Flagstaff in Arizona, he mapped out canals on Mars. We know that Mars has got polar caps. They thought perhaps a civilization might be living there, eking out what limited supplies of water there might be. Well, we know now that those canals don't actually exist. However, someone did in fact photograph a face on Mars not that long ago, perhaps 15 years, 20 years, and this is obviously a statue left behind to show us what the Martians looked like. But more recently, a much more detailed image has been taken. I think if you screw your eyes up, does it look a bit like a face still? But it isn't. It's a thing called a maser. It's got steep sides and a flat top. However, if there was a civilization there, they were obviously a very happy group of people. As we've got nearer with our spacecraft, we've seen giant canyons. This is called Valles Marineris. But also, here are two. There's actually 3 giant volcanoes. And just over the edge, Olympus Mons. It's the largest volcano we know of in the universe. The caldera is about 60 miles across. The overall size is 500 miles. And when these giant volcanoes were active, they don't just put lava and ash into the atmosphere, they put lots of gas. Ammonia, methane, water vapor, carbon dioxide. Carbon dioxide, water vapor, and methane are all so-called greenhouse gases. And when they were in the atmosphere, which obviously was a lot thicker, they made Mars much warmer than it is today. And we know that there was liquid water in the atmosphere, and we're absolutely certain now that, in fact, there was water on the surface. Way back in 1976, 2 Viking spacecraft went to search for evidence of life. Britain sent a spacecraft in 2003, Beagle 2, and I was charged with bringing back its very first signals to Earth, but sadly, it looks as though it crash-landed. But time will come when we do have a real chance to search for any past life on Mars. Spirit and Opportunity have been roving the Martian surface for a long time now, and they've shown us real evidence that there was once water there. And more than that, recently the Phoenix lander, which has sadly just died, but had a wonderful time on Mars for the last sort of 100 days or so, has dug a trench, and at the bottom it's actually shown ice. We've thought for a while that beneath the surface of Mars there was a permafrost. This is proof that there actually is. A few days later, that ice had gone, because in the low atmospheric pressure, it sublimates away, it turns into a gas. Now, you might think you have to be on the surface of a planet to have a chance to exist. Not necessarily so. Further out, we're way beyond the habitable zone, so how can it be warm enough? Well, when spacecraft started giving close-up images of Jupiter, seen here with its great red spot, and its moons, the Galilean moons, it found Io looking quite amazing. It's pockmarked with craters. There are active volcanoes on the surface of Io. So how can it be molten? Well, it's because it's very close to a giant planet, Jupiter, and tidal forces are racking the surface of Io. The tidal forces from the moon on the Earth's water raises the surface of the water, the oceans, by about 1 meter. Here, the surface of Io is going up and down by about 40 meters. And that's sort of squeezing and pulling the center of Io. It's molten because of that friction, and so it can have active volcanoes. Now, obviously, as you get further away from Jupiter, the tidal forces are less. And in complete contrast, Europa has an icy surface. You can see cracks in it. those are the results of the tidal forces. But when they took close-up images, it looks as though the surface is actually breaking up. Sort of icebergs. It appears that the surface, the icy surface of Europa, is floating on an ocean of liquid water. And as the surface breaks up, water comes up and then freezes. And you can see, I think if you look here, evidence that things have shifted and moved and broken apart. I haven't spotted the Titanic, but I could try. Now, if you've got an icy surface overlaying an ocean of water, it is not impossible that in that ocean there could be life. We suspect that life arose here on Earth close to what are called underwater hydrothermal vents, underwater hot springs, basically. It could be that there are underwater hot springs in that ocean, and it may be beneath that icy crust there is in fact life. Maybe someday, I suspect not in most of our lifetimes, a spacecraft will go and burrow down through the ice to see if it can find evidence of life there. So you don't necessarily have to be on the surface of a planet. That's the point I wanted to make. Well, are there other solar systems? Well, yes, there are. We've always suspected that there should be. Now we're actually beginning to discover them. The last sort of 10 years has been a wonderful period. We're up to about 300 odd planets now, and that number is increasing rapidly as more sophisticated instruments are used to try and detect them. One very odd thing is that quite a number of these planets are very large, larger than Jupiter, but very close to their star, not what was expected. And that will have some consequences I'll come to later on. In fact, a group, part of whom are at Jodrell Bank, have discovered the smallest planet we've found so far. It's 3 times the mass of the Earth. No one's yet discovered an Earth-sized planet, but we're getting close, and I think within the next 10 years we will have. This one could just about have water on the surface. And really quite excitingly, just a few weeks ago, the very first image of a solar system taken with a telescope on Earth, the star here has they've tried to remove it, so it looks a bit odd, but there are 1, 2, 3 planets. In fact, my next Gresham lecture at the end of January is all about the search for other worlds, so we'll come back to that then. So we now know there are lots of solar systems. What type they are, I'll come back to a little bit later. Could we detect the presence of any other life? Well, if in fact we can see a planet not too far away, it's been done already, we can actually measure the spectra of its atmosphere. We can learn about what's in the atmosphere. And just as an example, here are the spectra of 3 planets from our own solar system. Venus at the top shows you the presence of carbon dioxide. Not surprising, it's a very, very thick CO2 atmosphere. Mars down here, although the atmosphere is much thinner, is also very largely carbon dioxide. But the atmosphere of the Earth, if you measured it from a distance, a spectra, shows you carbon dioxide, all right, down here. It shows you water vapor, but it also shows you ozone, O3. And you can only have ozone in an atmosphere if you have free oxygen. Because oxygen is a very reactive compound, think of rust. My old Leyland cars used to turn into rust very quickly. But new cars are much better, aren't they? It's a good thing. Those of you who have been around a long time will know what I mean. That ozone can only be there if there's free oxygen. The free oxygen will only be there if it's being replenished. And we don't know many ways of replenishing oxygen apart from the presence of life. So if we found ozone in the spectra of the atmosphere of a distant planet, we'd know at least some form of life existed there. So let's just show where we are in our universe. Probably doesn't show up too well. It's a lovely view, in fact, of our Milky Way galaxy. It's a flat disk. It has a central bulge. All these dark regions, which I think you probably can see, they're not because there are no stars there. It's because there are great dust lanes largely made of carbon. The size of those carbon particles is almost exactly the same size as the carbon particulates that come out from badly maintained diesel cars sadly, or lorries and buses, not so many now, but you know what I mean, the cloud of black smoke that comes out when a badly maintained lorry starts up at some traffic lights. Happily, that's almost in the past. But you see, the point is that those sized dust particles, the carbon, very good at absorbing light. These, by the way, are two nearby galaxies called the Magellanic Clouds, and just over here is a giant galaxy, which I'll come to in just a minute. We know we have a central bulge, we have a very thin plane, a disk. It's about 100,000 light years across. This is the only image we have taken in the far infrared that actually shows our galaxy, the Milky Way galaxy, with its bulge and its flat disk. In Ireland, in the last century, 2 centuries ago, they built, the 3rd Earl of Ross built a wonderfully large telescope, 74 inches in aperture. And with this, he observed for the first time what is called the spiral structure of a galaxy. If you compare that with a modern-day picture, I think he did quite a good job, didn't he? We believe we live in a spiral galaxy too. And the most recent observations, literally just a couple of months ago, give us this as the most likely structure and shape of our galaxy. We obviously can't see it, but a wonderful spacecraft called Spitzer, observing in the infrared, can look through the dust, and this is the pattern it's got. We think we have a bar in the middle, 2 major spiral arms, and in fact our sun is here in a little sub-branch. It would be lovely to be able to see that from way away. Maybe somebody is giving a lecture somewhere else showing a picture of our galaxy. I don't know. The Andromeda Galaxy is our largest big neighbor. The light from it takes about 2.5 million years to reach us. You can see this with your unaided eye. I have a page called the Night Sky page on the Jodrell Bank website. If you put night sky into Google, it comes up probably top, amazingly. And on there is a little chart to show you how to find the Andromeda Galaxy. At a time of new moon, if it were clear tonight, it would be a lovely chance to see it. It'll be in the south around 10 o'clock at night. Quite easy to find if you know where to look. And you can see that with your own eyes. The photons, I love this, the photons that are falling on your retina, left there 2.5 million years ago. You're looking back into time. Astronomers really are the world's best historians by orders of magnitude. So that's the biggest galaxy. It's a bit bigger than us. We're number 2. This is another galaxy rather similar to Andromeda than our own. This is about 12 million light years away. Again, a spiral galaxy. This is a lovely one called the Sombrero Galaxy. It looks a bit like a Spanish hat. And that's about 14 million light years away. And this is probably very like our own galaxy. It's called Messier 83. And you can see there's a central little bar there. I don't know if it shows up on there. And these 2 major spiral arms. So very like our own Milky Way galaxy. And this compares a bit with that edge-on picture I showed you of our galaxy. There's the central bulge in the middle. You can see this thin disk. And you can actually see the dust lanes as well. So the same things that are happening in our galaxy, we see happening everywhere out in space, in the universe. Galaxies don't like to be by themselves. They're in groups or clusters. The clusters may up to have 1,000, 1,500 galaxies. And I suppose you could say the center of London was a giant cluster. And if so, there are smaller clusters surrounding it. And then right on the outskirts, you have rather smaller upmarket areas. I've sort of Red Hill, places like that. Well, we're like that. We're in what's called the local group, and we're on the very edge of our local supercluster. And our own group is one of the largest groups in our part of the universe. So we look out in the universe and we see the same sort of thing. Here's the Hercules cluster and the Hydra cluster. So everywhere we look, we see galaxies. This is one of the deepest images ever taken by the Hubble Space Telescope. And these are galaxies, some of which we're seeing almost as soon as they were created, perhaps 1,000 million years after the origin of the universe. We know now that our universe has a very lumpy structure. You can see some holes here. These are called voids. Gravity has that effect. Where things are denser, the gravity tends to pull in material from the less dense regions. So they get less dense, and the denser regions get more dense. So we have a lumpy, clumpy universe. I say that for a reason for later on. How old is the universe? Well, I may have got that wrong, but I don't know how many S's there should be in Ussher, but it may be odd. He was the primate of all Ireland between 1625 and 1656. And I'm sure you probably know he calculated the universe was created on the nightfall preceding the 23rd of October, 4004 BC. So it's about 6,000 years old. Now, we might laugh at that, but we shouldn't. He was a very educated man, and he did this scientifically. I mean, how do we work out the age of trees? We count the tree rings. What did he do? He worked out the genealogy of David. And if you read some of the early chapters of the Bible, there was a fair bit of begatting going on. I mean, do you remember Ashab begat Meshach? Well, basically, they're generations. And if you take an average age for a generation, I don't know, 20 years, you work out the number of generations, can you see you get the age? Now, I mean, if my students did this, I wouldn't argue. I would actually say that his error bars are a bit small, in that he sort of was a bit too precise, but nevertheless, there was nothing wrong in what he tried to do. Perhaps the premise behind his calculation wasn't actually right. How far back in time can we actually see? Well, in fact, there was radiation left over from the origin of our universe in what is called the Big Bang. It's called the cosmic microwave background. It was first discovered serendipitously by two Americans, Penzias and Wilson, using a radio telescope that was used in the very first satellite communication experiments. And they discovered this signal that they couldn't really understand why it should be there. It didn't matter where they looked, they still had this signal. A pair of pigeons lived inside here. They're quite nice places for pigeons to live. We have them on our telescope as well. Now, they're warm-blooded. They would produce noise. They could have been the cause of this noise that shouldn't have been there. Well, they put them in a trap. It's a very famous trap. It's now in the Air and Space Museum in Washington. They took them about 50 miles away and released them, and what happened? They flew back. So they had to get a local pigeon expert to remove them. Anyway, during their time in that horn, they had left behind what in their nature letter was called a white dielectric substance. We might call it guano or something else. That was cleaned out, but still no effect. And then, in fact, someone told them, aha, you have actually picked up the signal left over from the Big Bang. And as time has gone by, we've looked at this in more and more detail. We have telescopes up on Mount Teide in Tenerife. These are telescopes high in the Atacama Desert in Chile. And more recently, a spacecraft called MAP has actually made this map of the universe just 400,000 years after its origin. And the point to make is it also looks lumpy and bumpy. If it wasn't for that lumpiness, we couldn't be here because the galaxies couldn't have formed. But this gives us a sort of a starting point for the evolution of our universe. As I've told you, we know what it looks like now. We know what it was like then. We can put in the parameters, and we can actually work out what must have happened between. And that helps us give an age. We believe the universe was created in what we call a Big Bang, 13.6 to 13.7. That's better than 1% precision. That's pretty amazing for astronomers. 10% is usually pretty good. 1%, brilliant. 13, let's say 14,000 million years ago. How do we know this? Well, obviously the universe must be older than anything within it. We believe the oldest stars are somewhere between 12 and 13,000 million years old. The universe must be older. We know the rate at which the universe is expanding. We know how it's evolving. And we can extrapolate backwards in time until it had no size. That was when the Big Bang happened. That's when all the matter in the universe was created. Now, this is really a major part. Was the universe created by God? And there's one very significant fact. the universe is fit for the emergence of life. Otherwise, I could not be here talking to you. I've mentioned one or two things about the way the sun produces energy that have to be just right for stars to remain stable, to create a constant supply, roughly, of heat and light over the time scale required for evolution to happen. And there are quite a number of parameters, the velocity of light, ratios between the charge of the electron and the velocity of light, all of which affect how reactions happen. And quite honestly, if they were not very, very, very close to the actual values, we could not possibly be here. This universe has got just the right makeup to allow life to exist. Now, that's obviously true, otherwise I wouldn't be talking to you. But why is it true? How can it be that if physics or science or astronomy can't say why these parameters have the values they have, how can they have them? Well, there are only really two possibilities in my mind. I've just said here, there's nothing in the laws of physics that says the universe must be able to support life. If many of the fundamental constants of nature were not just right, we couldn't be here. So what are the two possibilities? Well, one is that the universe was created by what we might call a god, a creator, who set it up so the universe could support life. So it was designed so that life could actually arise. I don't, of course, believe in what some people call creationism. To me, it would be far better and more intelligent if you want an oak tree to make an acorn and let the acorn grow into an oak tree. So if you make the right conditions, hopefully we would arise anyway. You don't have to create us as individual beings. The other possibility is that there are myriads of universes, all with different properties, and of course the only people who will ever worry about it are those that can arise in a universe which just happens to be suitable for life. So this is called a multiverse. It's something put forward by a current Astronomer Royal, Sir Martin Rees. Now, some people say our universe has an enormous size and we only see so far. Beyond our horizon, the universe may have different properties. And so somewhere out there, the properties might not be right for life. They just happen to be here. Not sure I go for that one. The other possibility is that there are more dimensions in the universe than we know of. Perhaps that's not the right word. In the cosmos, I think I should say. The cosmos is all-enveloping. There are physics theories, string theory, which imply there might be more dimensions than the four we talk about, 3 of space, 1 of time. Many of them, there are 5 theories that have 10 dimensions. 6 of them, they're all curled up, and they form what are called strings, and the way those strings vibrate give rise to the different particles that make up the universe. A very clever man called Ed Witten. Has anyone heard of Ed Witten? 1 or 2. He's probably the most brilliant physicist in the world at the present time. He's managed to bring all of those theories together by saying, in fact, there are 11 dimensions, possibly more. And there's another dimension, at least, outside those that we can conceive of. And so here's an analogy. If I brought a sliced loaf, I could split up, let's say, 3 or 4 of the slices, slice, 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 slice. On each of those slices, I could put some ants. And I think they could probably survive there for a bit, eating the bread for a while anyway. Now, I don't know if ants can sort of see high up above them. They live in a 2-dimensional world, basically. And certainly, I think that the ants on one of these slices of bread would probably not know about the ants on this slice of bread here. To them, they'd be living on a 2-dimensional world, and that wouldn't worry them at all. But we, because we can see and think in 3 dimensions, can look down on that row of sliced bits of bread and see, in fact, that they are just 2-dimensional universes, in effect, within a larger 3-dimensional space. Do you get the idea? So it may well be that our universe is just one of myriads of universes that all coexist, but within an additional dimension. Well, I don't think there's any other way that we can tell whether that's the case or not. We can't say which of those 2 possibilities is true. So although I don't think science can say that God has to exist, it certainly cannot say a God or a creator does not exist. In my view, it's one of only two possibilities. So I think that's a very fair comment. How often might there be other people like us? I mean, you hear the chosen race in the Bible. Well, are we a chosen race? You see, a long, long time ago, it was thought that we were it, that our Earth was the center of the universe, that the planets went around the Earth, and so on. We were special. Then we discovered that there were thousands of stars and a universe with thousands and myriads of galaxies. And we got this sort of principle of mediocrity, the opposite, that we're nothing special, that the universe will be teeming with intelligent life. In fact, Carl Sagan, you might have heard of, 40 years ago, used to think that there might be 1 million advanced civilizations in our Milky Way galaxy. I think things have changed. I just want to take you through a calculation I did just last week as I was preparing this lecture. There's a very famous equation called the Drake equation, which I've actually modified. I'm not going to call it the Morrison equation, but it actually knocks out one term from the Drake equation. It adds another term which is relevant to our current understanding of solar systems. This looks horrible. N is that, sorry, that was not meant to happen. Press the wrong button there. N here on the left, that's the number of other civilizations that might exist in our galaxy at the present time. R is the rate of star formation, and these are parameters that actually indicate how likely it is various things will happen. So we'll go through them. It's quite easy, step by step. I'm going to start. I want to find out how often a civilization might arise, on average, in our galaxy. How often something like our own civilization might happen. We start with the number of stars born per year in the Milky Way. Even though there are 100,000 million stars in our galaxy, the number produced per year of new stars is only 7. I find that amazing. It's very small. So that's something we know. It's about the only thing we do know. Actually, there's one or two more things we know a bit. So we have 7. The number of stars per year is 7. But you see, not all of those stars will work. Some stars are too hot, and they burn up their fuel so quickly, they don't live long enough for life to evolve. Other stars are too cool. You can't get near enough to be warm enough. It turns out that most stars are not suitable, and only about 20% stars, similar of course to our sun, because we know that's right, are suitable. So can you see, of those 7 stars a year, perhaps one of them typically would be suitable in terms of its longevity and its heat. So we've reduced the number. So one suitable star might arise every 5 years. What fraction of those have got planets? Well, we don't yet know, but we're obviously beginning to discover planets. In fact, we're not really discovering as many as we thought we would, but I think that's because it's quite hard to discover planets, and the techniques haven't quite got right. I think there'll be a lot of planets to be discovered in the future. As time goes by, we'll discover many more. And my gut feeling is that probably 10% of all stars will have planetary systems. So I'm making a factor there of 1 in 10. So can you see, if we had one suitable star every 5 years, we'd have one star with a planetary system every 50 years. Do you see how I'm increasing the time? So we carry on doing that. Now, this is a new one. The fraction of stars with terrestrial planets, like our own. Well, we've discovered an awful lot of very massive planets, more massive than Jupiter, very close to their sun. We don't believe they can be formed there. We believe they must be formed roughly out where Jupiter is, which means they work their way in towards their sun. In doing so, they would throw out into space any terrestrial-type planets. So that's a slight worry. So I've got a fraction, which is the number of solar systems which will have terrestrial planets, like our own Mars, Earth, Venus. And I've put a factor in there for 1/10. I don't know the answer, but that's probably of order right. So these are things we sort of vaguely know of. How many of those planets, if you've got some terrestrial planets, will be in a habitable zone? Well, in our case, there's one, seems quite a good example, so I put one there. That's great. Doesn't affect things. The fraction of habitable planets where life arises. Now, of course, we don't know. What we do know, though, is that life arose here on planet Earth virtually the instant the Earth could support life. So if it can happen easily here, there's no real reason why it can't happen easily elsewhere if the conditions are right. So I'm going to be optimistic, and I'm going to say that everywhere where life could arise, it will. And so I've got another factor of 1. Do you see where we're going? Okay, now, this is the real clincher, and it's the thing we really don't know. How often will simple life, that arose so easily apparently on the Earth, evolve into advanced, intelligent life like us? This is the most difficult part of this equation to estimate. Now, as I said, 40 years ago, people like Carl Sagan said that if you've got simple life, evolution will drive it towards intelligent life. Well, I'm not so sure. Our Earth is perhaps rather special. In fact, there's a lovely book called Rare Earth. Quite a lot of things are going on and have gone on that have enabled the temperature on the Earth to remain stable. Volcanoes, plate tectonics have played a major role because carbon dioxide forms carbonates. It gets dissolved in the oceans. Little animals form crusts. So over time, the amount of carbon dioxide in the atmosphere would tend to fall. Now, I know we don't like carbon dioxide, but if it wasn't there, we'd be too cold. We couldn't be here. You do need some global warming. Otherwise, it'd be far too cold for us. If that CO2 leaves the atmosphere, the Earth will get colder. Now, of course, those little shells of those animals, gradually, when they die, sink down to the ocean floor. And you may know that in the oceans, there are oceanic plates that move outwards. And when they reach the rather lighter material of the continental plates here, they go underneath a process called subduction. And you get volcanoes. They call the Ring of Fire around the Pacific. And in fact, that brings that CO2 back into the atmosphere. So the Earth, because of that, has helped maintain a relatively stable temperature. We have a pretty big moon. And that, in fact, has stabilized the Earth's rotation axis. It varies by just a little bit. Otherwise, you could get flips, and the poles could very quickly become the equator and vice versa. And life would have a job to actually cope with that. Comets are lovely things, as we shall see. This is a most beautiful painting. I'm sure you've seen it, The Adoration of the Magi by Giotto di Bondone. He had seen Halley's Comet, I think in 1306, and in 1303, in 1306 to 9, during that time he produced this lovely icon. And here you can actually see Halley's Comet, which he thought might be the Star of Bethlehem. This is a lovely comet we call Hale-Bopp. It was in 1999, perhaps the most beautiful we've seen for a long time. But of course, they are good and they are bad. They are good because in the past they may well have brought about a third of our water to the Earth. Comets are icy snowballs. They contain lots of ice and hence obviously water. But of course they can impact the Earth and they can upset things. It may well be that the dinosaurs were wiped out about 65 million years ago from the impact of a comet over the Yucatan Peninsula of Mexico. Now, that was a good thing for us, wasn't it? Because that allowed the little mammals to evolve into us. And that's another problem. It's possible that you could have a life form that we would not say was intelligent, depending how you define it, but certainly not like us, that could be so well adapted to its environment, it prevents any evolution beyond. So even if you have good, stable conditions for a long time, it doesn't necessarily mean that an intelligent life form like us will evolve. But if you have too many comets, they can upset us too much for much to happen. If you had a company, you could have management consultants come in perhaps every 10 years to make things work better. But if you brought management consultants in every year, it would cause chaos. Some of you are laughing, you probably know. Anyway, the point is this: our Jupiter has prevented the majority of comets that would hit the Earth from hitting us. So we've had a number of comets, that's a good thing, but not too many to stop us being here. So there are really quite a number of things that tell us that our Earth is really rather special. So I have no idea how often simple life will evolve into advanced life. It's really difficult to estimate. But I put a number of 1 in 10,000. I don't know if that's true or not. It could be more often than that. It could be a lot less than that. But I don't think every simple life form will develop into an intelligent civilization. And I think a lot of people share that view. So this really has a major effect. If you multiply all these things together, how often might intelligent life arise? That's the big one here. It turns out to be 35 million years. And we don't really know how accurate that is. But the point is this: if that were true, unless a civilization like us can last for 35 million years on average, do you think that's going to happen? I'm not sure. Then, in fact, it is quite likely that we are the only advanced civilization in our galaxy at the present time. I seriously do not believe that our galaxy is teeming with intelligent life. Okay, there are myriads of galaxies. There'll be life like us, advanced, out there somewhere, but perhaps not that close. So, I've just said this. If the lifetime of a civilization is longer, unless it's longer than 35 million years, then we may be the only advanced civilization in the galaxy at the present time. Perhaps our human race really is a bit special. They thought that a few thousand years ago, a couple of thousand years ago. We've thought that perhaps we're nothing special. Maybe now we should begin to regard ourselves as being a bit special. I do hope it might make us think of preserving our planet and ourselves a bit better than we seem to be doing at present, but there's not much I can do about that. But just my final comments. Are we perhaps here for a purpose? I might dare give a Gresham lecture on the quantum universe someday, on quantum physics. And one interpretation of quantum physics is that unless you can observe something, it doesn't actually happen. Quantum states only actually take up a real state unless it's seen. And some physicists say that our universe couldn't exist unless there's somebody observing it, which perhaps is us. So perhaps it only is here because we're here looking at it, which is very odd. I don't really believe that. But let's think about this. If you did think that our universe was perhaps the first of my two possibilities, produced by a creator God. I mean, if you were a musician, a composer, or an artist, what is the point of making a beautiful painting or a lovely symphony orchestra unless someone can appreciate it? I've shown you, I hope, some of the lovely images of our universe. It is a very beautiful place. It could just be that we are here to appreciate the beauties of a universe created by God. Thank you for listening. Can I come down?